1954. Obninsk, Soviet Union. Engineers in white coats gather around a control panel. Outside the window, it's an ordinary autumn day. But inside this building, something is happening that the world has never seen before. They close a valve, and for the first time in history, steam from a nuclear reactor is directed toward a turbine. White clouds of ordinary steam hissing from the pipes look like a miracle. The scientific director, Igor Kurchatov, shakes hands with his colleagues and congratulates them on a nice little steam bath, as if they had just started up a new boiler, not the world's first device that turns a split atom into electricity for homes, factories, and hospitals. There are tears in some eyes. But this miracle, this moment when humanity first made the atom work for it, was not the culmination of a long and clear plan. It was a tangle of coincidences that wove themselves into a tight knot, and no one was controlling the process.
Why do we have nuclear energy at all? Not because someone wisely planned the future, but because one physicist, who foresaw this power before anyone else, couldn't read his own handwriting after a sleepless night in London. Because in Paris, it rained for several days, and one scientist decided to develop a photographic plate simply out of curiosity. Because the man who was supposed to lead the most expensive project in history dreamed of being anywhere but on this assignment. Today, nuclear energy seems to us like the logical outcome of scientific progress. But if you think the story of how humanity tamed the atom is a story of rational planning, you're wrong. It's a story of how chance, personal choice, and inevitability intertwined into one tight knot. We'll trace this chain of coincidences that led us into the atomic age, because to understand why we live in a world where the atom serves us, we first need to understand how we even found out it existed.
And for that, we have to go back 100 years, to one cloudy week in Paris, where rain changed the course of history. At the end of the 19th century, physicists were confident that the world was almost fully understood. It seemed that the main laws of nature had already been discovered, and all that remained was to refine the details. Newton had given mechanics. Maxwell had given the theory of electricity and magnetism. Mendeleev's periodic table arranged the elements in orderly rows. The universe looked like a clockwork mechanism that just needed to be studied down to its last tiny screw. But there were small anomalies, small puzzles that didn't fit this picture. One of them concerned mysterious rays emitted by certain substances, and in 1895, the German physicist Wilhelm Röntgen discovered that his experimental tube emitted something capable of passing through paper, wood, and even human flesh, leaving shadows of bones on photographic plates. He called this unknown radiation X-rays. X as in the unknown. The world was stunned. For the first time, it was possible to look inside a living person without cutting them open. Doctors saw broken bones, bullets in soldiers' bodies. It was a miracle. But this miracle raised a question. What else can emit invisible rays? And that question led Henri Becquerel to his fateful experiment in Paris. Becquerel came from a family of scientists. His father and grandfather were professors who studied phosphorescence, the glow that remains in a substance after it has been exposed to light. Henri Becquerel decided to test whether phosphorescent substances emitted X-rays. He took crystals of uranium salt. They glowed in the dark after being in the sun. Then he wrapped a photographic plate in thick black paper so that no light could reach it. On top of the paper, he placed the uranium crystals and put everything out in the sunlight. His idea was simple. Uranium absorbs solar energy and then re-emits it as penetrating rays that expose the plate through the paper. The experiment worked. The plate was exposed. Becquerel concluded that his hypothesis was correct. and reported his preliminary results to the French Academy of Sciences on February 24, 1896. But then, the weather turned bad. For several days, the sky was overcast and there was no sun. Without sunlight, Becquerel couldn't continue his experiment. He put the prepared plates and uranium crystals in a desk drawer and decided to wait. February 27, 1896. Paris was still gloomy. Becquerel opened the drawer and took out the plates. And here is where this story becomes great. Logically, there should have been no image on the plates. After all, the uranium had received no solar energy.
But Becquerel, whether out of scientific curiosity, impatience, or because he needed something to report at the next Academy meeting, decided to develop the plate. And he saw something incredible. The silhouette of the uranium crystals on the plate was clear and strong, even stronger than on the plates that had been exposed to sunlight. Uranium emitted rays on its own. It didn't need sunlight. It didn't need any external energy. It glowed with an invisible light constantly, giving off energy whose origin was completely unclear. From this moment on, physics ceased to be almost complete. Becquerel had discovered not just a new radiation. He had discovered that atoms can change. They can spontaneously decay, emitting particles and energy. He had discovered radioactivity, although the word itself would come later. But as often happens, Becquerel didn't fully understand what he had found. He was a bit confused and soon moved away from the topic.
However, his discovery did not go unnoticed. In Paris, in the same city, a young Polish physicist named Marie Skłodowska-Curie and her husband Pierre decided to study Becquerel's mysterious rays. In 1898, they began a systematic study that led them to the discovery of two new radioactive elements, polonium and radium. Radium was so radioactive that it glowed in the dark and was warm to the touch. Marie Curie coined the term radioactivity. But working with radium was dangerous. She carried test tubes of radium in her pocket, unaware that the radiation was destroying her body. She would die of aplastic anemia caused by radiation exposure. But at the beginning of the 20th century, no one understood this danger. Radioactivity seemed like an endless source of mysterious energy, and nothing more. The atom seemed inexhaustible. But no one knew how to make it give up its energy, until a New Zealander decided to look inside the atom and see what it was made of.
Ernest Rutherford was one of those people who seemed born to overturn our understanding of the world. In 1909, together with his assistants Hans Geiger and Ernest Marsden, he conducted an experiment that was supposed to confirm the existing model of the atom, the plum pudding model proposed by J.J. Thomson. According to this model, the atom was a sphere of uniform positive charge, inside which negatively charged electrons were embedded like raisins in a pudding. Rutherford decided to test this model by firing alpha particles, the nuclei of helium atoms emitted by radioactive elements, at an extremely thin sheet of gold foil. It was expected that the alpha particles would pass through the foil, slightly deflected from their path. After all, in Thomson's model, there was nothing dense in the atom that could stop or strongly deflect a fast particle. And most of the alpha particles did pass through the foil with almost no deflection. But about 1 in 8,000 particles behaved completely differently. It bounced back, as if it had hit an impassable barrier. Rutherford later said it was like firing a 15-inch naval shell at a sheet of tissue paper and having the shell come back and hit you. It was a shock. But Rutherford understood what it meant. The atom was not a pudding. Almost all of its mass and all of its positive charge were concentrated in a tiny region at the center. Rutherford called this region the nucleus.
The atom, it turned out, was mostly empty space. If you scaled it up to the size of a football stadium, the nucleus would be the size of a grain of sand on the 50-yard line. But that grain of sand contains almost all of the atom's mass, and it is held together by forces that, pound for pound, are millions of times stronger than any chemical bond. This is where the key lies. In this incredibly dense, tiny region is the energy that can power cities. But how do you get to it?
How do you make the nucleus give up its energy? For that, you need a key. And that key was found in 1932, when James Chadwick at Cambridge discovered a particle with no electric charge, the neutron. The neutron could penetrate the very heart of the atom without being repelled by its electric field. It was the perfect battering ram for storming the nucleus. Now, humanity had not only a lock, the uranium nucleus, but also a key, the neutron. All that remained was to understand what would happen when you put the key in the lock. And that was understood by a woman who had been forced to flee her homeland, escaping the Nazis. By the end of 1938, a group of physicists at the Kaiser Wilhelm Institute for Chemistry in Berlin was bombarding uranium with neutrons. The chemist Otto Hahn and his colleague Fritz Strassmann were getting results that didn't fit any theory. Instead of creating new, heavier elements, which they expected to get, so-called transuranic elements, they found barium. Barium has an atomic number of 56. Uranium has 92. Barium is roughly half of uranium. Hahn was baffled. He was a chemist, and his chemical methods told him it was barium. But his physical intuition screamed that it was impossible. An atom couldn't just fall apart into two pieces. He wrote a letter to his old colleague Lise Meitner, who was now in Sweden, having been forced to flee Nazi Germany. Meitner received Hahn's letter on Christmas Eve, 1938. She was shocked. She knew the chemical precision of Hahn and Strassmann, and she knew their results couldn't be an error. But she couldn't understand how it was possible. Then her nephew, Otto Frisch, came to visit her for Christmas in the small Swedish town of Kungälv. They went for a walk. Frisch on skis, Meitner walking briskly beside him. And during this walk through the snowy forest, Meitner had a flash of insight. She remembered the liquid drop model that Niels Bohr had previously proposed for describing the nucleus. The nucleus could be imagined as a drop of liquid held together by surface tension. In the case of the nucleus, the strong nuclear force. But the uranium drop was a very large and unstable drop. The protons in it repelled each other electrically, and this repulsion was almost at the limit beyond which the drop would break apart. Now imagine that a neutron hits this overloaded drop. It brings additional energy. The drop begins to oscillate, stretch, and if the oscillations are strong enough, it pinches in the middle, like an overstretched rubber band, and breaks into two smaller drops. Meitner and Frisch stopped on the forest road. They took a piece of paper and started calculating. They used Einstein's famous equation E equals mc squared.
They calculated the mass of the original uranium nucleus and the mass of the two resulting fragments, barium and, presumably, krypton. It turned out that the mass of the fragments was slightly less than the mass of the original nucleus. This lost mass was converted into energy according to Einstein's formula, and the energy they got was staggering, about 200 million electron volts per fission event. That's roughly 10 times more energy than any other nuclear process, and millions of times more than the energy released in a chemical reaction, like burning coal. They realized they had discovered a new process. Frisch, remembering the biological term for cell division, called it fission. Meitner and Frisch wrote an article for the journal Nature in which they proposed a theoretical explanation for what had happened. It was published on February 11, 1939.
When news of uranium fission spread around the world, physicists realized something much more important than just a new type of nuclear reaction. They realized that when a uranium nucleus splits, it releases not only energy, but also 2 or 3 additional neutrons. These secondary neutrons could, in turn, strike other uranium nuclei, causing them to fission, which would release even more neutrons, and so on. The possibility of a chain reaction emerged. One fission event triggers the next, which triggers the next, and so on, potentially without end. This idea of a chain reaction was both exciting and terrifying. In human hands, it could become a source of inexhaustible energy, or a weapon of unprecedented destructive power. Both were possible. Physicists around the world began frantically working on how to control this chain reaction, or how to make it uncontrollable.
In those days, as the world stood on the brink of World War II, and Nazi Germany had already invaded Poland, a Hungarian physicist sitting in London reading a newspaper realized that time was the only thing humanity no longer had, and that if he didn't act, the monstrous power hidden in the atom could fall into Hitler's hands. News of the chain reaction spread around the world at the speed of light, and at that same moment, several physicists, including a Hungarian reading a newspaper in London, understood what had to become inevitable. The chain reaction was not just a physical phenomenon. It was a matter of life and death for entire nations. September 1933, London, the intersection of Southampton Row and Russell Square. An ordinary grey day, ordinary people hurrying about their business, cars waiting for the light to turn green. A Hungarian physicist named Leo Szilard stands on the sidewalk, waiting for the green light. In his coat pocket is a copy of the London newspaper, carrying the text of a speech by Ernest Rutherford. Rutherford, the very man who showed that the atom is mostly empty space with a tiny nucleus, had declared the day before that talk of getting energy from atoms was moonshine. Szilard crosses the road, and in the middle of the intersection, an idea strikes him. An idea that will change the world. Why were we able to build the nuclear bomb and the nuclear power plant at all? Because one man was crossing a road and thinking about how Rutherford's words sounded. Because he asked himself a question that others didn't even want to consider. What if a neutron, when it hits a nucleus, releases not 1, but 2 new neutrons? The chain reaction is not just a physical concept. It is an idea born on an ordinary London intersection in the head of a man fleeing the Nazis. We will trace how one idea, one thought that came to a random pedestrian, made the greatest physicist of the century write a letter to the president, and then how that idea turned into a machine capable of either providing humanity with energy for centuries or destroying it. Because in this intersection lies the whole essence of our story. Here, chance met inevitability. Leo Szilard was not just a physicist. He was one of those people who seem born to see what others cannot. And he was a very strange man. He was born in Budapest in 1898, the son of a Jewish engineer, and from an early age showed an extraordinary ability to think unconventionally. He completed his university studies in Berlin, where he studied with the greatest minds of his time: Planck, Einstein, von Lauer. But an academic career didn't appeal to him. Instead of publishing articles in prestigious journals, he spent his time on inventions. By 1933, he had 29 patents, including several created jointly with Einstein. And characteristically, many of these patents were for everyday items. For example, household refrigerators that used thermoelectricity instead of dangerous ammonia vapors. Szilard was interested in everything related to energy conversion. He was looking for ways to use energy more efficiently. That's why, when the neutron was discovered in 1932, Szilard began to wonder,
What if you directed this particle at the nucleus? What if you could use a neutron to break the atom and release its energy? It was pure speculation, a mental exercise. But this time his imagination was working in the right direction. But in 1933, the Nazis came to power in Germany. Szilard was Jewish. He had to flee. First he went to Vienna, then to London. And it was in London, in September 1933, that he stumbled upon a newspaper article that changed his life.
The article quoted a speech by Ernest Rutherford. Rutherford, who himself had looked inside the atom and seen its nucleus, said, "Anyone who looks for a source of energy in the transformation of atoms is talking nonsense." He called it moonshine. The irony was that Rutherford didn't deny the possibility of getting energy from atoms as such. He denied its practical realization in the foreseeable future. He believed that humanity didn't have enough intelligence or technology to do it. But for Szilard, Rutherford's words sounded like a challenge. He was walking down the street, crossing the intersection, and suddenly the idea hit him. He realized that Rutherford was wrong. If a nucleus split by a neutron emits not one but two neutrons, then these two neutrons could split two more nuclei, which would emit four neutrons, and so on. A chain reaction. And if you start it, energy will be released that cannot be stopped, until the fuel runs out.
Szilard later recalled,
"While I was waiting for the light to change, and when the light changed to green and I crossed the street, it suddenly occurred to me that if we could find an element which is split by neutrons and which emits two neutrons when it absorbs one, then such an element, if assembled in sufficiently large mass, could sustain a nuclear chain reaction." At that moment, in the middle of a London intersection, Szilard invented the atomic bomb. He didn't know which element would work. He didn't know how to practically implement this idea. But the concept itself, the possibility of a chain reaction, was formulated. This was the moment when theory turned into possibility. Szilard was not just a theoretician, he was a man of action. As soon as the idea took shape, he began to act. He went to laboratories, began looking for ways to test his hypothesis. But he encountered incomprehension. No one took him seriously. His idea seemed too fantastic, too far from reality.
So Szilard did what he always did. He patented it.
In 1936, he transferred the patent for the chain reaction to the British Admiralty. He understood that this idea could be used for military purposes and wanted to keep it out of the hands of potential enemies. The British government classified the patent. It was perhaps the first attempt in history to control a technology that hadn't yet been created. But Szilard didn't just patent ideas. He looked for ways to implement them. He understood that a chain reaction required two things: a suitable element and a sufficient quantity of it. He needed to find an element that, when split, emitted more neutrons than it absorbed. And he needed to collect it in a critical mass, an amount sufficient for the reaction to sustain itself. But in the 1930s, no one knew which element was suitable. Uranium seemed like a possible candidate, but no one was sure.
Physicists bombarded uranium with neutrons, but the results were confusing. No one understood what was happening inside the nucleus. And then other heroes entered the scene. Leo Szilard was not alone. In the 1930s, a group of outstanding scientists of Hungarian origin emerged in Europe and the United States, who played a key role in the nuclear program. They were called the Martians for their incredible intelligence and ability to think unconventionally. Besides Szilard, this group included Edward Teller, Eugene Wigner, John von Neumann, and Leo Szilard himself. All of them had fled Europe, escaping Nazism. When the discovery of uranium fission became known in 1939, Szilard and his colleagues realized that the chain reaction was no longer just a theory, it was real. The neutrons emitted during fission could start a chain reaction in uranium, and if so, then an atomic bomb was possible. But there was one problem. Germany had already begun work on a nuclear program. German physicists were among the best in the world. If Hitler got the atomic bomb first, the consequences for the world would be catastrophic. Szilard and his colleagues, especially Edward Teller and Eugene Wigner, concluded that they urgently needed to warn the American government. But how? They were not known in political circles. Their words had no weight. And then they remembered the man who could reach the president, Albert Einstein. July 16th, 1939, a Saturday. Wigner and Szilard got into a car and drove to Long Island, to Einstein's summer cottage. Einstein was the most famous scientist in the world. Everyone knew his name. If he signed the letter, it would be read. Einstein was welcoming. He knew Szilard. They had even worked together on patents. Szilard explained the situation. A chain reaction in uranium was possible, and Germany might start work on a bomb.
Einstein immediately grasped the essence. He agreed to sign the letter. Szilard and Einstein spent several hours working on the text. Einstein was not directly involved in nuclear research, but his authority was undeniable. The letter they drafted stated, "In the course of the last 4 months, it has been made probable that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type, carried by a ship and exploded in a port, might very well destroy the whole port, together with some of the surrounding territory." The letter ended with a warning about Germany. "I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines, which she has taken over." Einstein signed the letter on August 2, 1939. But delivering it to the president was not easy. Szilard and his colleagues found a financial expert named Alexander Sachs, who had connections in the White House. Sachs was to deliver the letter to Roosevelt, but Roosevelt was busy. War was looming in Europe. Germany had already invaded Poland. The world stood on the brink of catastrophe. Einstein's letter sat with Sachs for more than a month. Only on October 11, 1939, did Sachs get an audience with the president. Roosevelt read the letter. He understood its seriousness and created the Uranium Advisory Committee. Later, this would lead to the creation of the Manhattan Project, but don't think that after this work went into full swing. The first steps were tentative. The committee allocated $6,000 for experiments to create a chain reaction. $6,000 for what would become the most expensive project in history. This was clearly not enough to catch up with the Germans. By the end of 1939, the situation was as follows. First, uranium fission had been discovered and confirmed experimentally. Second, it had been established that fission releases additional neutrons that can trigger a chain reaction. Third, it was understood that for a chain reaction you needed uranium-235, not uranium-238, and you needed to separate it from uranium-238, which was complex and expensive. Fourth, they understood that a moderator was needed to slow down the neutrons, and there were candidates: graphite, water, heavy water. Fifth, the United States had created the Uranium Advisory Committee, but with a very modest budget. Meanwhile, research was also being conducted in Germany, England, France, and the Soviet Union. But the main problem was that no one knew how to actually implement a chain reaction.
Research was being conducted in different laboratories, often isolated from each other, and only a few understood the scale of what was possible. Enrico Fermi, an Italian physicist who had fled fascism to America, began working on creating a chain reaction at Columbia University in New York. Together with Szilard and other scientists, he began building a reactor, a pile of graphite and uranium that was supposed to reach criticality. Fermi and Szilard conducted a series of experiments, gradually increasing the amount of uranium and graphite, approaching the critical point. They didn't know whether a chain reaction would occur or not. It was a gamble. They were risking not only money, but also their reputations. But soon it became clear that the experiments required much larger scales.
The graphite had to be ultra-pure, without impurities that would absorb neutrons. Uranium was needed in large quantities. Money was needed, and organization was needed. In 1941, the American government realized that the uranium bomb was real. The Manhattan Project was created. But before that, there was one more important milestone. In 1942, Fermi and his team faced a choice. They could continue building the reactor in New York, but it was risky and expensive. Or they could move the work to Chicago, where there was more space and less attention. They chose Chicago. And there, under the stands of the abandoned Stagfield Stadium, they built what would go down in history as Chicago Pile 1. It was a structure of graphite and uranium that was supposed to become the world's first nuclear reactor. On December 2, 1942, scientists gathered under the stadium stands. Fermi, holding a notebook and pencil in his hands, began slowly withdrawing the cadmium rod, the control rod that regulated the reaction rate. The Geiger counters began clicking faster and faster. The reaction was building. Fermi stopped. He looked at the instrument readings and told his colleagues that the reaction was self-sustaining. He had proven that a chain reaction was possible. It was a triumph. But Szilard, standing nearby, was not rejoicing. He knew what this meant. He knew that this reaction, the very one he had imagined on the London crosswalk, was now real. And it could be used to create weapons. Szilard turned to Fermi and said, "This day will go down in history as the day when man first used atomic energy. And I hope it will not go down in history as the day when man destroyed himself." The next step was already inevitable. From proving the possibility of a chain reaction to building a bomb was just one step. On December 2, 1942, scientists under the stands of the Chicago Stadium started the world's first self-sustaining chain reaction. They did it manually, without any automation, using cadmium rods, and stopped the reaction when they realized it was starting to grow. It was a moment of triumph and at the same time terror. Szilard, standing next to Fermi, knew. He had crossed the road on the London crosswalk, and now there was no turning back. The chain reaction was real. Now only one thing remained: to build the bomb. But for that, billions of dollars were needed, entire factory cities, and military discipline that would turn theory into weapons. And here, a man who was not a physicist, but who took responsibility for creating the atomic bomb, enters the scene. His name was Leslie Groves, and he didn't want to take on this project. September 1942, Washington, D.C. Colonel Leslie Groves has just received news that has shattered all his plans. Instead of going to the front, commanding troops in battle, he has been put in charge of a project that his own superior called a hopeless gamble: to develop an atomic bomb in 3 years, before the Nazis do. Groves is not a physicist. He is an engineer, a builder, the man who constructed the Pentagon. And he has just met the man he wants to make his chief scientist. A thin, absent-minded professor from Berkeley who has never managed even a university department, let alone a secret laboratory. Who doesn't know how to hammer a nail, who has ties to communists, whom the security service considers a threat. No one understands this choice. No one except Groves himself. Why was the atomic bomb created in America and not in Germany, where it was discovered? Why did a project that was supposed to fail become the greatest engineering triumph in history? Because one man, called the biggest son of a bitch in the army, met another man, called a hopeless dreamer.
And they understood each other. They formed a union that seemed impossible, but it was precisely this union that made the atomic bomb a reality. We will trace how this incredible duo, a military engineer and a theoretical physicist, overcame distrust, bureaucracy, and logic itself to create a weapon that changed the world. Because in this story, full of chance and inevitability, their meeting was perhaps the most important coincidence of all. September 17th, 1942. Colonel Leslie Richard Groves sits in his office in the War Department building in Washington. He is 46 years old, heavy-set, blunt, and not used to being contradicted. Behind him is the construction of the Pentagon, the largest office building in the world. He managed 1 million workers, spent billions of dollars, and did it with iron efficiency. But right now, he is irritated. Irritated to the core. He has been promoted to Brigadier General, but instead of being sent to Europe, to war, where he could prove himself as a commander, he is being put in charge of the Manhattan Project. A secret, pointless as it seemed to him, project to create an atomic bomb. He had heard about it. Everyone had heard about it, but no one believed it would work. Even his superior, Major General Wilhelm Steyr, told him it was a hopeless undertaking. Groves was a military engineer. He built bridges, roads, airfields. He knew how to manage people and materials, but physics, quantum mechanics, nuclear fission, these were beyond his understanding. And he was going to have to lead scientists who spoke a language he didn't understand and considered military men to be little more than idiots. But Groves was not just a soldier. He was a man who understood one simple thing. If you take something on, you need to do it well.
And he decided that if he was destined to lead this project, he would make it the largest and most secret undertaking in human history. The first thing he did was insist on his promotion to general. Scientists won't respect a colonel, he told his superiors. He got his brigadier general's star and got to work. Groves's plan was audacious to the point of madness. He intended to create 3 enormous industrial complexes simultaneously, even before it was proven that a chain reaction was possible at all. One in Oak Ridge, Tennessee, for uranium enrichment. A second in Hanford, Washington, for plutonium production. A third in Los Alamos, New Mexico, for designing the bomb itself. The problem was that he didn't know if it would work. No one knew. Physicists were arguing. Some said a chain reaction was impossible. Others said it would destroy the world. Still others said it would work, but would take decades. Groves didn't listen. He built. But to build the bomb, he needed a scientist. And not just any scientist, a leader. Someone who could manage America's brightest minds, persuade them to work together despite ambitions and disagreements. Someone who could translate the most complex physics into language the military could understand. And Groves found such a man. Robert Oppenheimer was the complete opposite of Groves. Thin, pale, with perpetually disheveled hair and a cigarette that almost never went out. He was a theoretical physicist, a man who lived in a world of abstractions. He didn't know how to hammer a nail, didn't know how to drive a car, and could often be seen wandering through the Berkeley campus in deep thought, completely oblivious to his surroundings. He was brilliant and charismatic. His students adored him. His colleagues respected him. But he had no administrative experience. He had never run a laboratory. He was an absent-minded professor who could forget a meeting with the university president because he was thinking about quantum mechanics.
And he had a past. His brother was a member of the Communist Party. His wife was too, his own wife. He himself had been involved with left-wing groups. Military intelligence was horrified. They considered Oppenheimer a threat to national security. And yet Groves chose him. When Groves announced his decision to the military committee, they told him it was madness. He won't make it, they said. He's unreliable. He can't lead. But Groves stood his ground. He saw something in Oppenheimer that others didn't. He saw a man who understood physics deeply enough to see the whole picture, a man who could speak to scientists in their language while simultaneously understanding military requirements, a man who was willing to take responsibility. Groves later wrote, Oppenheimer had two serious shortcomings. He had almost no administrative experience, and he was not a Nobel laureate. But I have never considered my choice of him a mistake. Oppenheimer, in turn, saw in Groves a man who could do the impossible. He understood that without military support, without resources, without iron discipline, the project would fail. He knew that physicists were chaos and they needed to be organized. Together they formed an incredible pair, a military engineer who didn't understand physics and a physicist who couldn't manage. But they complemented each other. While Groves and Oppenheimer were planning the future, in Chicago a group of scientists was already building the past. Or rather, they were building the future in the basement of an abandoned stadium. Enrico Fermi, the Italian physicist who had fled fascism, was one of the few people in the world who knew how to build a nuclear reactor. He knew that a chain reaction required a moderator, a material that slows down neutrons. He chose graphite, pure graphite. But there wasn't enough pure graphite. There wasn't enough uranium either, and Fermi didn't know if it would work. And yet he built, layer by layer, graphite, uranium, graphite, uranium. Under the stands of Stagg Field in Chicago, in the very center of the city. Without radiation shielding, without cooling systems, just a pile of graphite and uranium that could either start a chain reaction or melt down and poison all of Chicago. Arthur Compton, the director of the metallurgical laboratory where Fermi worked, was horrified. He wanted to build the reactor in the Argonne Forest, 25 miles from the city, where it would be safer. But construction there was delayed. Fermi insisted on starting in Chicago. He was confident in his calculations. He knew the reaction wouldn't get out of control. Compton hesitated. But on December 2nd, 1942, he made his decision. He gave Fermi permission to start the reactor. Morning, December 2nd, 1942. 49 people gathered under the stands of Stagg Field. Fermi stood at the control panel. Next to him was Walter Zinn, his executive director, as Alvin Weinberg would later call him. Zinn held an axe in his hands. If the reaction got out of control, he was supposed to cut the rope holding the cadmium zip rod, which would absorb neutrons and stop the reaction. It was Plan B, and it was highly undesirable. Fermi began slowly withdrawing the cadmium rods. The Geiger counters clicked faster and faster. The crowd of physicists watched tensely. At 11:30 in the morning, Fermi ordered the zip rod to be withdrawn to a certain level. The reaction was building, but the counters showed that criticality had not yet been reached. Fermi stopped. He had a sandwich, discussed the results with his colleagues, and continued. By 3:20 in the afternoon, he had withdrawn the last rod. The counters went wild. The needles on the instruments jumped. The reaction was self-sustaining. The chain reaction had begun. Fermi waited 28 minutes. Then he signaled to Zinn. Zinn cut the rope. The cadmium rod fell into the reactor. The reaction stopped. It was over. The chain reaction was real. Arthur Compton called James Conant, the head of the National Defense Research Committee. and spoke the coded phrase. "The Italian navigator has arrived in the New World." Conant asked, "How are the natives?" Compton replied, "Very friendly." It was a triumph. But it was also the moment when the future became inevitable. On December 2nd, 1942, under the stands of the Chicago Stadium, humanity started the world's first self-sustaining chain reaction. It was the moment when atomic energy ceased to be theory. It became reality. But Fermi and his team did more than just prove physical possibility. They showed that the reaction could be controlled, that man could start a chain reaction, manage it, and stop it. This was the key that opened the door not only to the bomb, but also to peaceful atomic energy. Now Groves and Oppenheimer faced a new task: to turn this spark into a weapon. And for that, they needed to build factories that could produce enough uranium and plutonium for a bomb. Factories that would dwarf anything man had ever built. Groves had already started acting. He bought land in Tennessee and Washington. He hired tens of thousands of workers. He built cities that existed only on maps. All of this for a weapon that hadn't yet been created. The next step was to build the reactor itself that could produce plutonium on an industrial scale. And here, Groves faced a problem that nearly doomed the entire project. The problem was that no one knew how to cool such a reactor. It would operate at full power. It would generate enormous amounts of heat. And if it wasn't cooled, it would melt down. Engineers proposed several options: helium cooling, water cooling, liquid sodium cooling. No one knew which would work. Groves did what he always did. He ordered all options to be built simultaneously. "Even wrong decisions are better than no decisions," he said. "Time is more valuable than money." 1943, the desert of Washington State. Tens of thousands of workers are frantically building a city that doesn't exist on any map. They are erecting giant concrete buildings, laying miles of pipe, drilling wells for water from the Columbia River. They don't know what they're building. They're told it's a military project, but no one explains the details. Some think it's going to be a rubber factory. Others think it's a secret aircraft plant. 1,000 miles to the east, in Tennessee, a similar scene. Another ghost town, another tens of thousands of workers, another billions of dollars. They're building factories that will enrich uranium, but none of them know what uranium enrichment is. They just follow instructions. And in New Mexico, in the desert, a group of young physicists is trying to figure out how to make plutonium explode. The problem is that all these projects are connected. Uranium is needed for plutonium. Plutonium is needed for the bomb. The bomb is needed for the war. But none of these projects can wait for another. All of them must be completed simultaneously, and no one knows if it will work. Why was the atomic bomb created so quickly? Because one man decided to build factories before the chain reaction had even been proven possible. Because he understood. Time is more valuable than money. Because he hired a company that made explosives to build nuclear reactors. We will trace how America's industrial machine was rebuilt in a matter of months to produce the impossible. Enough uranium and plutonium for a bomb. How ordinary workers, many of whom had never seen an atom, became part of the greatest engineering project in history. Because the Manhattan Project is not just about physicists. It is the story of how the full power of American industry was directed toward creating a weapon that changed the world. Fall 1942. General Leslie Groves sits in his office and looks at a map of the United States. He needs to find locations for 3 giant factories that will produce components for the atomic bomb. And he has 3 requirements: remoteness from major cities, access to water and electricity, and, most importantly, secrecy. The first place he chose was in Tennessee, in the Clinch River Valley. It was a region of hills and farms with a population of about 3,000 people. Groves bought 260 square kilometers of land, almost 100 square miles.
Residents were given a few weeks to pack up and leave. Many farmers, whose families had lived on this land for generations, were forced to leave their homes with minimal compensation. Groves named the place Oak Ridge.
But it wasn't on any map. It was a ghost town that was supposed to become the center of uranium-235 production. The second place he chose was in Washington state, on the banks of the Columbia River. It was a desert region known as Hanford. Here there was water, the Columbia River, which could cool the reactors. Here there was electricity, from the Grand Coulee and Bonneville dams. And here there was isolation, 600 square miles of desert where they could build without prying eyes. Groves bought that land too. Another 400,000 acres. Another thousands of farmers forced to leave their homes. Another ghost town created on maps that no one saw. The third place he chose was in New Mexico, on the Los Alamos Plateau. It was a private boys' school. Groves bought it and turned it into a secret laboratory. Now Groves had 3 locations, but they meant nothing without people who could build them. Groves knew he couldn't build these factories himself.
He needed a company that had experience building giant industrial facilities, and he knew which company was right for the job: DuPont. DuPont was known as an explosives manufacturer, but it also had another kind of experience, managing complex chemical processes on an industrial scale. Groves invited DuPont representatives to a meeting in Washington. He told them, "We're building a secret project. We can't tell you what it is, but we want you to build several factories for us." DuPont agreed, and it was a risky decision. DuPont wasn't a nuclear company. It didn't know about radioactivity. It didn't know about plutonium. But it had experience building factories, and that was enough. Groves signed a contract with DuPont to manage the Hanford complex. It was an unprecedented move. DuPont was supposed to build reactors to produce plutonium, but no one knew how to do that. DuPont had to invent the process on the fly. And that wasn't the only problem. Time was critical. Groves gave DuPont exactly 2 years to build the factories and start plutonium production. It was unrealistic. Normally, building such a factory takes 10 years. But Groves said, "Time is more valuable than money." And DuPont got to work. In Oak Ridge, construction proceeded at a frantic pace. In 1942, there were 3,000 residents. By 1945, the population had grown to 75,000 people. It was the 4th largest city in Tennessee, built in just 2 years. The city was completely secret. It wasn't on any map. It didn't have a name, just a number, X-10. Entry to the city was controlled by the military. Workers lived in barracks and dormitories, segregated by race. They worked 24 hours a day, 7 days a week. They were paid well, but they didn't know what they were building. Oak Ridge had 3 main factories. First, Y-12, the electromagnetic separator built to Ernest Lawrence's design. This factory used giant magnets to separate uranium isotopes. The magnets were so large that they required 14,700 tons of silver from the US Treasury. The silver was melted down and wound into coils. After the war, the silver was returned, but not all of it. Some magnets remained in Oak Ridge. Second, K-25, the gaseous diffusion plant. This was the largest factory in the world at the time. It covered 44 acres and consumed more electricity than the entire state of Tennessee. The factory used thousands of tons of uranium hexafluoride, which was turned into a gas and passed through membranes. The process was incredibly slow and expensive, but it worked. Third, S-50, the thermal diffusion plant. This was an experiment designed to help enrich uranium for the other factories. It worked by exploiting temperature differences that separated isotopes. This plant was a supplement to the main ones, but it accelerated the process. These 3 factories together
formed the basis of uranium-235 production for the Little Boy bomb. But their construction was a nightmare. Thousands of workers labored in dangerous conditions with toxic chemicals and radioactive materials. Many of them got sick. Some died. But they kept working. In Hanford, the situation was even more complex. Reactors for plutonium production were being built there. The reactors were larger than anything ever built. Each reactor was the size of a small power plant. They required enormous amounts of water from the Columbia River for cooling, and they produced plutonium, which was needed for the Fat Man bomb. But there was one problem. No one knew how to work with plutonium. Scientists in Los Alamos were trying to figure out how to make plutonium explode, but they didn't know if it would work. In September 1944, the first reactor in Hanford, B reactor, was ready for startup. DuPont engineers and the physicists working on the project gathered around the control panel. They were confident the reactor would work. Calculations showed that the chain reaction would start as soon as they withdrew the control rods. They withdrew the rods. The Geiger counters began to click. The reactor was building power. Everything was going according to plan. And then the reactor stopped. Power dropped. The reaction ceased. No one knew what had happened. The calculations were correct. The design was right. But the reactor wasn't working. Engineers were baffled. They checked everything. The control rods, the cooling, the fuel, everything was in order. But the reactor wasn't working. Enrico Fermi, who was in Chicago monitoring the project by phone, understood what had happened. He remembered xenon poisoning. Xenon-135 is a decay product of iodine-135, which forms in the reactor during uranium fission.
Xenon has an enormous neutron capture cross-section. It absorbs neutrons, preventing them from participating in the chain reaction. In a normal reactor, xenon is burned off by neutrons, but in the new reactor, too much had accumulated. The reactor had been poisoned. Fermi realized they needed to increase the amount of uranium in the reactor, but DuPont had already built the reactor with a certain number of fuel channels. There were 1,500 of them. Fermi said they needed to add another 500 channels to compensate for the xenon losses. DuPont agreed. But it meant rebuilding the reactor. It meant delay. It meant plutonium would be produced later than planned. But DuPont had no choice. Construction of the factories in Oak Ridge and Hanford was proceeding at full speed. But in Los Alamos, in the New Mexico desert, a group of physicists faced a problem that could destroy the entire project. The plutonium they were receiving from Hanford was radioactive, and it was unstable. When they tried to build a bomb, they discovered that plutonium spontaneously emits neutrons. This meant that if they assembled a critical mass of plutonium, it could explode prematurely, before it was ready. They needed a different approach. They needed a bomb that could compress faster than plutonium could emit neutrons. They needed implosion, an inward-directed explosion that would compress the plutonium to critical density. But no one knew how to do it. Implosion was complex. It required perfect symmetry. If the explosion wasn't perfectly spherical, the plutonium would simply fly apart without reaching critical density. And here, a man who knew how to work with explosives entered the picture. He was a chemist, an explosives specialist, and he was ready to take the risk. His name was George Kistiakowsky. July 1944, Los Alamos, New Mexico. A group of physicists gathers in Robert Oppenheimer's office. On the table lies a report from Emilio Segre. The news he brings destroys 2 years of work. The plutonium they plan to use in the gun-type bomb spontaneously emits too many neutrons. If they try to fire one piece of plutonium into another, the bomb will detonate prematurely. It won't work. It will just fizzle, scattering radioactive material but producing no nuclear explosion. The gun-type design is dead, at least for plutonium. Silence fills the room.
Someone suggests abandoning the plutonium bomb. Someone else suggests trying to enrich the plutonium to remove impurities. But Oppenheimer knows there is no time. The war is on. Germany is still fighting. If they want to win, they need another path. And that path is called implosion. Why was the most complex bomb in history created in just a few months? Because a group of scientists and engineers faced an impossible problem and solved it using genius, desperation, and incredible luck. Implosion is not just another way to set off a bomb. It is completely new physics.
Instead of firing one piece of material into another, they have to make explosives compress plutonium from all sides simultaneously, with precision down to microseconds and thousandths of an inch. We will follow how an émigré chemist, a Hungarian mathematician, and a group of young physicists turned the impossible into reality. How they learned to control an explosion, making it work for them, and how they created a weapon that changed the world. Because implosion is the story of how humanity learned to trick nature itself. To understand why implosion became necessary, we need to go back to April 1944. That was when Emilio Segre, an Italian physicist working at Los Alamos, received the first sample of plutonium produced in the Hanford reactor. Until that moment, all plutonium research had been conducted with material produced in a cyclotron, a particle accelerator. That plutonium was pure, almost without impurities. But reactor plutonium turned out to be different. Segre and his team measured the spontaneous fission rate of plutonium-240, an isotope that inevitably forms in the reactor when plutonium-239 captures another neutron. The result was devastating. The spontaneous fission rate was tens of times higher than for pure plutonium-239. This meant that any piece of reactor plutonium constantly emits neutrons. For the gun-type design, this was fatal. The gun-type design works like this. You take a subcritical mass of plutonium, place it at the end of a barrel, and fire another subcritical mass into it. When they come together, a critical mass forms, and the chain reaction begins. But the entire assembly process takes about a millisecond, an eternity by nuclear standards. During that time, spontaneous neutrons from plutonium-240 can trigger the chain reaction prematurely, when the material hasn't yet fully assembled. The bomb will fizzle, a small nuclear explosion that scatters the material but doesn't produce a full-scale detonation. Oppenheimer called an emergency meeting. The decision was made quickly and ruthlessly. The gun-type design for plutonium was cancelled. All efforts were redirected to implosion. But there was one problem. Implosion was far more complex. No one knew if it would work. The idea of implosion wasn't new. As early as 1942, physicist Seth Neddermeyer had proposed using explosives to compress plutonium. But at the time it seemed too complex. Instead of firing one piece into another, you had to make explosives compress plutonium from all sides simultaneously. And that compression had to be perfectly symmetrical. Neddermeyer worked on the idea alone, and his experiments were discouraging. When he detonated explosive tubes, they compressed unevenly, turning into shapeless lumps of metal. Most scientists considered implosion a hopeless endeavor. Only Neddermeyer believed in it. But the situation changed when John von Neumann arrived at Los Alamos. The Hungarian mathematician, one of the most brilliant minds of the 20th century, was brought in as a consultant. He looked at the implosion problem with fresh eyes and realized that not only was it possible, but it had a huge advantage. Von Neumann showed that implosion could compress plutonium to twice its normal density. Denser material requires a smaller critical mass. This meant less plutonium was needed for the bomb. But more importantly, the compression would happen faster than the gun-type assembly. If the explosives were designed correctly, the compression would take microseconds, too little time for spontaneous neutrons to trigger a premature reaction. Von Neumann also proposed the idea of
explosive lenses, devices that could transform a diverging detonation wave into a converging one, much like an optical lens transforms diverging light into converging light.
But for this, they needed an explosives expert. And that expert was George Kistiakowsky. George Kistiakowsky was born in Kiev in 1900 into a family of Ukrainian Cossacks who belonged to the intellectual elite of pre-revolutionary Russia. In 1917, during the Russian Revolution, he was forced to flee. He fought in the White Army, then escaped Russia on a French ship, traveling through Turkey, Yugoslavia, and Germany before receiving his doctorate in physical chemistry from the University of Berlin in 1925. By 1930, he was a professor at Princeton and later at Harvard. Kistiakowsky was not just a scientist, he was a practitioner. He knew explosives from the inside out. During World War II, he headed the Explosives Research Laboratory and worked on shaped charges, devices that focus the energy of an explosion into a narrow jet. This experience proved invaluable for the project.
When von Neumann proposed the idea of explosive lenses, Oppenheimer immediately thought of Kistiakowsky. In October 1943, Kistiakowsky was invited to Los Alamos as a consultant. He immediately understood the scale of the task. The problem was that explosives are not a precision instrument. They are brute force. They destroy, they don't create. But Kistiakowsky believed that explosives could be controlled. He told von Neumann, "Explosives are a controlled, precise mechanism, not just a blind, destructive force." And he got to work. The idea of explosive lenses was simple in theory, but devilishly complex in practice. An explosive lens consists of two different explosives, a fast one and a slow one. The fast explosive, such as composition B, has a high detonation velocity. The slow explosive, barytol, has a low velocity. When a detonator triggers the explosion in the fast explosive, the wave travels outward.
But at the boundary between the fast and slow explosive, the wave slows down. If the shape of that boundary is chosen correctly, a diverging spherical wave can be transformed into a converging one. The wave reaches the outer surface of the lens simultaneously across its entire area, exactly like an optical lens focuses light. Kistiakowsky faced enormous difficulties. First, the lenses had to be manufactured with precision down to thousandths of an inch. Second, they had to be assembled into a sphere, about 32 lenses, each of a unique shape. Third, all the detonators had to fire simultaneously, with a spread of no more than a microsecond. Kistiakowsky and his team worked around the clock. They cast the lenses from molten explosive, then machined them to the required shape. But the casting precision wasn't good enough. They needed molds with precision that civilian contractors couldn't provide. Kistiakowsky later recalled, "The greatest torment was getting molds of the required precision from suppliers outside Los Alamos. In the end, they found a solution. They used molds made in the Los Alamos workshops and cast each lens by hand. It was slow, agonizing, and required inhuman precision. But it worked. By April 1945, the first lenses were ready. But there was another problem. While Kistiakowsky worked on the explosives, another group of scientists was trying to solve the problem of the plutonium itself. Plutonium is a temperamental metal. It exists in 6 different crystalline phases, each with its own density and properties. At room temperature, it is in the alpha phase, brittle and hard. When heated, it transitions through beta, gamma, delta, and epsilon phases. This variability made its processing extremely difficult.
The original plan called for creating a hollow sphere of plutonium. When the explosion compressed this sphere, it would collapse into a solid ball of high density. But this required perfect symmetry. Even a small deviation could cause the sphere to collapse unevenly, and the bomb wouldn't work. In 1944, physicist Robert Christie proposed an alternative. Use a solid sphere of plutonium instead of a hollow one. The solid sphere was smaller, but it didn't need to be compressed as much. It was enough to increase its density by 20 to 30% to reach critical mass. This idea simplified the task. Instead of creating a perfect sphere that collapsed with microscopic precision, they could use a solid ball that was simply compressed to a higher density. The solid ball was easier to manufacture and less sensitive to asymmetry in the explosion. The Christie design, called the Christie gadget, was adopted in early 1945. Now they had a plutonium core that could be manufactured, but there remained the problem of the neutron initiator, the device that had to trigger the chain reaction at the right moment. The neutron initiator was a critical element. It had to provide a burst of neutrons at the moment when the plutonium reached maximum density. If the neutrons appeared too early, the bomb would detonate prematurely. If too late, the reaction wouldn't start. The initiator was developed by a team led by Charles Critchfield. It was a tiny device placed at the center of the plutonium sphere. It consisted of two hemispheres, one of beryllium, the other of a polonium-beryllium alloy. When the explosive wave compressed the initiator, the polonium and beryllium mixed, and the alpha particles from the polonium triggered a nuclear reaction in the beryllium, which emitted neutrons. The initiator was made from polonium, which was produced in Dayton, Ohio, by the Monsanto Chemical Company. Polonium was extremely radioactive and dangerous. Working with it required the utmost caution. But the initiator worked, and by July 1945, everything was ready. By the summer of 1945, all the elements were in place. The plutonium core had been manufactured at Los Alamos. The explosive lenses had been cast and tested. The detonators had been calibrated. The initiator was ready. But there was still one problem. No one knew if it would work. Implosion had never been tested at full scale. Theoretical calculations said it should work, but theory was no guarantee. Oppenheimer and Groves made the decision. The bomb had to be tested. The test, codenamed Trinity, was scheduled for July 16, 1945, in the New Mexico desert at the Alamogordo test site. It was a risky decision. If the bomb didn't work, they would lose precious plutonium and precious time. But they had to know. On July 14, 1945, the gadget, as the test device was called, was lifted onto a 100-foot steel tower in the Jornada del Muerto desert. Kistiakowsky personally inspected every lens, every detonator. He spent hours removing the smallest defects, knowing that even a tiny air bubble or scratch could destroy the symmetry of the explosion. On the night of July 16th, the weather turned bad. A thunderstorm broke over the desert. Lightning struck the ground. The wind reached hurricane force. Groves wanted to postpone the test, but the meteorologist promised that the weather would improve by dawn. At 5:29 in the morning on July 16, 1945, the countdown reached 0. In the New Mexico desert, 200 miles from Los Alamos, a group of scientists and soldiers waited for dawn. They stood 10 miles from the concrete tower on top of which the gadget, the world's first plutonium bomb, was mounted. Kistiakowsky, who had spent the last hours checking every detail, stood silent. He knew that everything depended on whether the explosive lenses worked. If they worked perfectly, the plutonium would compress to critical density, and a nuclear explosion would occur. If not, the bomb would fly apart, producing nothing more than a conventional explosion. He didn't know what would happen in the next few seconds.
At 5:29 and 45 seconds in the morning, the clocks on the control panel showed 0. A blinding flash, brighter than 1,000 suns, lit up the desert. A wave of heat struck the observers 10 miles away. The shock wave, reaching them a minute later, knocked people to the ground. And over the desert rose a mushroom cloud, the symbol of a new era. Kistiakowsky watched and thought about what he had seen. He would later say, "I am sure that at the end of the world, in the last millisecond of the Earth's existence, the last man will see the same thing we saw."
The Trinity test was a success. Implosion had worked. But it was only the first step. Now they had a bomb, and in 3 weeks it would be dropped on a city. But that is a story for the next chapter. July 16th, 1945, 5:29 in the morning. The Jornada del Muerto Desert, New Mexico. A group of scientists and soldiers stands at an observation post 10 miles from a steel tower on top of which sits the Gadget, the world's first plutonium bomb. They have been waiting for this moment for years. They spent $2 billion, built entire cities, risked their lives and their sanity. And now, finally, the countdown has reached 0. A blinding flash, brighter than 1,000 suns, lights up the desert. A wave of heat hits the observers. The shock wave, reaching them a minute later, knocks people to the ground. And over the desert rises a mushroom cloud, the symbol of a new era. Someone laughs. Someone cries.
James Conant, the president of Harvard, briefly thinks that the atmosphere has caught fire and the world has ended. Oppenheimer, standing nearby, recalls a line from an ancient Indian epic. "Now I am become death, the destroyer of worlds." Why was the atomic bomb used? And why, after that, did humanity not stop, but instead continue to develop nuclear energy? Trinity was a success, but it was only the first step. In 3 weeks, bombs would fall on Hiroshima and Nagasaki. The war would end, but something new would begin. An arms race and, simultaneously, a struggle for the peaceful atom. We will trace how the greatest act of destruction gave birth to hope for limitless energy. How the scientists who created the weapon tried to prevent its use. And how the peaceful atom, born from the ashes of war, became a symbol of a new future. Because the history of nuclear energy is not just the history of the bomb. It is the story of how humanity learned to use a force capable of destroying the world to turn on the lights. Trinity was a success. Implosion had worked. The plutonium core compressed to critical density, and the chain reaction released energy equivalent to 21,000 tons of TNT. The steel tower on which the bomb was mounted had vaporized. The sand beneath it turned into a greenish glass, trinitite, which can still be found at the test site today. But for the scientists standing 10 miles away, this was not just a successful test. It was the realization that they had created something beyond human control. They saw the mushroom cloud rising to 7.5 miles into the atmosphere and understood the world would never be the same. Oppenheimer, who had led the project, later recalled, "We knew the world would not be the same. A few people laughed, a few people cried, most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita.
Vishnu is trying to persuade the prince that he should do his duty, and to impress him, takes on his multi-armed form and says, 'Now I am become death, the destroyer of worlds.'" But not everyone shared his poetic vision. Kenneth Bainbridge, the test director, walked up to Oppenheimer and said something more prosaic. "Now we are all sons of bitches." This comment reflected the guilt that many scientists felt. At the same time, in Chicago, hundreds of miles from the desert, the physicist Leo Szilard, who had first envisioned the chain reaction, received news of the successful test. He was not happy. He knew the bomb would be used against people. He began collecting signatures for a petition to President Truman, urging him not to use nuclear weapons against cities. But it was already too late. The machine had been set in motion, and nothing could stop it. After Trinity, the Americans had two bombs, one uranium gun-type bomb and one plutonium implosion bomb. The uranium bomb, codenamed Little Boy, was simpler. It didn't require testing. But the plutonium bomb, Fat Man, was more complex. Trinity had proven that implosion worked, but no one knew if it would work under real combat conditions. On August 6, 1945, the B-29 bomber Enola Gay dropped Little Boy on Hiroshima. The bomb exploded at an altitude of about 2,000 feet above the city. The flash blinded everyone who looked in its direction. The shockwave destroyed 70% of the buildings. The temperature at the epicenter reached about 7,000 degrees Fahrenheit. People within about 500 yards of the epicenter were instantly vaporized. Approximately 80,000 people died that day. By the end of the year, the death toll had reached 140,000. 3 days later, on August 9th, the B-29 bomber Boxcar dropped Fat Man on Nagasaki. The original target was the city of Kokura, but clouds interfered. Nagasaki became the secondary target. The explosion killed approximately 40,000 people that day, and another 40,000 died from the effects in the following months. Japan announced its surrender on August 15, 1945. World War II was over. But for the scientists who had built the bomb, this was not a triumph. It was a tragedy. The physicist Isidore Rabi, who had witnessed Trinity, said, "In that moment, I felt that we had become a threat to all life on the planet." After Japan's surrender, a new battle began, not against an enemy, but within the scientific community itself. The scientists of Los Alamos split into two camps. Some, like Edward Teller, believed the bomb should be developed further to deter the Soviet Union. Others, like Leo Szilard, advocated for control over nuclear weapons. But there was a third voice, the voice of Niels Bohr, the Danish physicist who had escaped from occupied Denmark in 1943. Bohr came to Los Alamos in 1944 and spent several months discussing the future of atomic energy with the scientists. He spoke about how the bomb had created a new political reality. Every great and deep difficulty bears in itself its own solution, Bohr taught. Bohr believed that the international cooperation within the Manhattan Project was an example of what could be achieved. He called for the creation of an open world, without secrets and arms races. He said that the only alternative was a race in which many countries would participate, making the world increasingly unsafe. Bohr tried to convey his ideas to Roosevelt and Churchill in 1944, but they had already agreed in Quebec in August 1943 to keep atomic secrets to themselves. The United States and Great Britain were determined to maintain a monopoly on atomic weapons. But Bohr didn't give up. He continued to insist that atomic energy should be an international asset. His ideas foreshadowed the creation of the International Atomic Energy Agency, IAEA, in 1957. On December 8, 1953, President Dwight Eisenhower delivered a speech before the United Nations General Assembly. This speech, known as Atoms for Peace, changed the course of history. Eisenhower proposed creating an international agency that would control atomic materials and promote their use for peaceful purposes. He also proposed that the United States and the Soviet Union contribute some of their uranium and plutonium to this fund for use in medicine, agriculture, and energy. But behind this noble proposal stood realpolitik. The Eisenhower administration wanted to prevent the spread of nuclear weapons by offering an alternative, the peaceful atom. They also wanted to use atomic energy to strengthen alliances and contain Soviet influence. Eisenhower's speech was met with enthusiasm. In 1954, the US Congress passed the Atomic Energy Act, which allowed the use of atomic energy for civilian purposes. Programs were created for training personnel, building research reactors, and medical applications of radioisotopes. But the Soviet Union was not idle. They were already working on their own atomic projects, and in 1954, they beat everyone to it. On June 27, 1954, in Obninsk, a small town southwest of Moscow, the world's first nuclear power plant went into operation. It was not just an experimental reactor, it was a working station connected to the electrical grid. Its capacity was 5 megawatts, enough to power a small city. The reactor was unique. It was based on a research reactor design, but its primary purpose was peaceful. The Soviet scientists understood that atomic energy could become not just a weapon, but a source of clean, cheap energy. The Obninsk plant became a symbol of a new world.
In the decade after its opening, the station was visited by about 39,000 people from 65 countries, including prime ministers, presidents, and leaders of liberation movements. Jawaharlal Nehru, India's first prime minister, visited the station with his daughter Indira Gandhi in 1955. Sukarno, the president of Indonesia, visited in 1956. Ho Chi Minh, the president of the Democratic Republic of Vietnam, and Kim Il-sung of North Korea were also among the visitors. For the Soviet Union, Obninsk was not just an engineering achievement. It was a propaganda victory. They were the first to show the world that atomic energy could serve humanity. It was a response to the American nuclear program, the peaceful atom as an alternative to the atomic bomb. But behind this propaganda success lay real science. Engineers faced many problems. The reactor required about 1,200 pounds of fuel, including about 61 pounds of uranium-235, enriched to 5%. It was experimental, and many of its systems were unreliable. In 1959, there was an accident, a rupture of the fuel cladding. But the station continued to operate, and it became the prototype for all future nuclear power plants in the Soviet Union. Obninsk was the first step, but it was also a symbol of the division in the nuclear world. On one side stood the United States, which had used the atomic bomb against Japan and continued to build up its arsenal. On the other side stood the Soviet Union, which, having built the bomb, sought to show the world that atomic energy could be peaceful. The arms race continued, but now it was joined by a race for the peaceful atom. Every country wanted to prove that it could use atomic energy not just for destruction, but for creation. And in this confrontation, a new era was born. An era in which nuclear energy became part of our daily lives. An era that began with one man crossing a road in London and led to a world where we use the power capable of destroying cities to turn on the lights in our homes. But the path was long, and it continues to this day. Because nuclear energy is not just a bomb and not just a power plant. It is a question of how we as people use the force we have created. And that question remains open.